I'd like to welcome our next speaker. It's Dr. Rajat Mani Thomas, who will discuss how to apply systems thinking to design agentic AI workflows that are context-aware, adaptive, and robust in real clinical settings. Dr. Thomas is a distinguished faculty in AI at Weill Cornell Medicine, where he leads the Thomas Lab for AI in Healthcare. He holds a PhD in computational astrophysics with subsequent work in neuroscience, AI, and health. He was also a co-founder of a very successful agriculture AI company. Please join me in welcoming Dr. Thomas.
Thank you, Shadab, and the rest of the organization committee for inviting me. It's a pleasure, and I know that I stand between you and lunch, so I will try to make it entertaining as well. And I'm very excited to talk about this topic, and it is far from any exposition of all the stuff that we have already done. But mostly, I'm going to use you as a sounding board for some of the ideas that will be brought up here. So feel free to be critical, give me feedback, and suggest alternatives, and we'll go on this journey together. Before I begin, I'll say that I'm from Weill Cornell, as an extension of Weill Cornell in Doha. This is about half an hour flight from here across the Arabian Gulf, and you'll reach here. It was established about 20 years ago as a premier institute for medical training. And in the recent years, it's become a hub for biomedical research within the country, and hopefully we'll collaborate in the wider region. So you all have become experts in agentic AI because you had so many talks until now, and we want to do a bit of exercise, like physical exercise. So I want you to tell me the answer to this question: which one do you think is more agentic? What you're seeing on your left is a squirrel, if you don't know, and on the right is a simple thermostat, the ones you change your temperature in your room. So show of hands who says that the squirrel is actually more agentic. There's no right or wrong answer. Show of hands for the thermostat is more agentic. Okay, it seems like we have a clear majority for the squirrel. We'll just go through some of the properties of these two elements. We start with the sense. Of course, both the squirrel and the thermostat can sense. The thermostat can sense just the temperature. The squirrel can sense all kinds of different things, olfactory, tactile, so on and so forth. Both can act, definitely. The thermostat can then ask the AC to turn on or turn off. But when it comes to planning, squirrel, I would say, is much more clever. So it can decide what to do for itself on a longer time scale, right? Whereas the thermostat is pretty static in that sense. And in terms of use, as you can see, the squirrels are very good. If you've seen some of them, they can take the nut and just break it. And they can use all kinds of tools to get their job done. But the thermostat is not, all right? So an agent really, apart from the agentic AI systems that we'll get into, is something, back from my neuroscience days, something that can sense, it can model, it can decide, and it can act upon the world. And it has a good understanding of what the world and the surrounding physics and chemistry of the world is, which often is referred to as the world model, right? So to build an agentic system, we need to think like brains, but really, we have to become systems engineer. I will motivate this all throughout my talk. So to set the stage, I want to say we've talked a lot about LLMs, but if you know the way LLMs are trained and why the companies spend billions of dollars continuously improving it, because a given LLM is a snapshot, if you wish, at best, of static intelligence, of static knowledge, right? It suffers from all kinds of problems. I've listed some of them here. Contextual fragility, or we say contextual junk. It depends. You've heard of LLMs that have very large context. That means you put the whole book in there and ask a question. And when you start, so first of all, the context that are often mentioned in the press is not the real context. There are a lot of kinds of patterns behind designing them. Then, of course, that knowledge, as I said, is static, right? It is not evolving unless you, again, spend billions of dollars fine-tuning it over and over again. It doesn't have a notion of goal. It just has to answer you, right? So essentially what it is, it's a powerful linguistic mirror, okay? It's not a reasoning agent, although we argue there are reasoning LLMs, but essentially what they do is traverse through some latent space of static intelligence. So you can start with a few things. Very interesting question. Again, show of hands. Don't look at the graph if you can, but I know now that I said that you will look at the graph. But what is the last digit of a sequence of lots of ones and zero? That's question number one. And what is the first digit of 0 and a whole sequence of ones? What do you think the LLM would answer correctly? The first question about the last digit or the second question about the first digit? Sorry that I have the answer up there. So it turns out, unlike the humans, intuitively you would say, if I tell you a sequence, 1, 2, 3, 8, 5, 6, blah, 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 and at the end I give you one word, the last token or the last digit, you're going to remember the last digit. That's very human nature. Oh, I forget what you told earlier on. The LLMs, it happens the other way. If you start with the 0 and a sequence of ones, it'll always give you a good 0. So you can see on the right now you can look at it, and you say, as the sequence length increases, when the sequence is short, it gets the first and the second digit right. But as you go further down, it only gets the first digit right, okay? Why is that the case? We'll just go through, this is like the least technical of it all. So most of the current LLMs are built in an autoregressive fashion, okay? So this is a general sort of information flow pathway. What you see on the very left is your input, tokens or words or whatever. Then it propagates through different layers of the neural networks. Especially, think of something like a transformer architecture, and you produce the next token, right? And it turns out that if you look at the embedding of the sequences, 1 or 2 ones or 3 ones or 4, and if you look at like lots of ones, what happens is that inside the latent space or inside the brain of the transformer, those sequences, when it gets really large, occupies a very, very compact space. And when that space becomes less than machine precision, which happens very quickly, actually, then you have a confusion between what's happening, okay? And the reason why this is happening is if you can look at it, the first tokens have an unfair advantage. They can go through many different sort of information pathways in the architecture. And the last one, of course, is the least seen. So the chance of that information propagating throughout the network is very large, right? And this issue not only is about just copying, and you can imagine that copying is one of the most basic things, right? And if a system cannot copy A to B, how do you expect it to do massive calculations, right? And it has a strawberry problem. This is very common in this LLM world, where you ask the LLM to count the number of R's in the word strawberry, it often gets it wrong, okay? As funny as that might sound, if you ask it to count the number of ones, again, the sequence, a very simple operation. Just you can write a 2-line Python code to do this. But if you ask it to count the number of ones, it gets it wrong invariably. Maybe in the sequence length is small, it gets it right. If it's too large, it invariably gets it wrong. We're talking about largish models here. And if it doesn't know, if it gets too large, it will just say 100. Whatever you give it, it says it has 100 ones, okay? And stop bothering me. That's what it'll say, right? So that was a technical mathematical issue, okay? Fine. We'll try to figure it out. But this extends also to sort of social problems. So one thing we are interested, my lab is also to build very robust and reliable agents or LLMs for guidance, for mental health, and so on and so forth. And this problem is not old, right? We are talking about a few months ago that a team killed himself, right? Because he managed to talk to ChatGPT, and even though they are funded in the billions of dollars, the team was able to crack the guardrails, and ChatGPT basically facilitated in his suicide, right? So this is a dangerous game. So now, what do you say? Let's go the other way. Big models are bad. You don't want to use one big model to do everything. Let's break it down. Let's have control. So previous speaker nicely explained the advantages of going to small language models, SLMs, as bias and so on. But at the end, it uses less energy. But small language models are easier to train because you don't need you don't need the entire internet to train a small language model. So we can say, okay, let's break it up into different parts. Let's train one agent to do just one task in one specific domain, and it becomes really good at it. It doesn't hallucinate, right? It doesn't have some of these other issues of energy and so on. But we needed to feed it with good quality data, okay? Good quality, pristine data, which is expensive, but you don't need a lot of it. Context is relatively small, so you can pack it with relevant information instead of like garbage in most of the context. And then you can build systems where you say, okay, instead of this big Goliath that we have, we'll build very small Davids, each one good at a particular task, and compose them together, all right? So the path then to true intelligence, you would say, is through this kind of a structure, right? Not big sizes, but small SLMs that do the job. And then you can embody these SLMs with tool use. So one of the small language models can be really good at calculating stuff, using the calculator to do things, right? The other one can write a piece of code to do particular analysis that you want, biomedical analysis of some sort, right? He understands genetics very well, and it can do that. And some of these things that we are working on, right? So if you take these small language models, give them tools, give them a very specific goal, and they're able to do good work. So agentic AI then transforms these large language models, which are just saying stuff, to something that can actually do things together. So we have solved the problem, and I can stop talking and go home. But the problem is far from being solved, right? So each one is very good. It's like when I asked to design a rocket in my previous life, this was part of my job to do systems engineering for satellites and spacecrafts. And if you have different teams that don't talk to each other, and one team has said, oh, build a good thruster. You say, okay, I'll put a wheel and thrust, and I go really fast. And the other team, I want the astronauts to sit comfortably. He'll build a jacuzzi. And all of these individual elements are not too bad. If you put the teams together and they don't talk to each other, you will end up with nonsense, right? So in compound systems, the other way of calling these agentic systems, compound systems, each of the elements of those compound systems are not bad. When you put them together, you get something which is completely misaligned, expensive, it breaks. And before we go into systems thinking, a philosophical thought that often you've heard of this concept of a evil corporation. You'll be surprised to know that evil corporations are generally not made of evil people. They are well-intended people, a lot of them put together, but then you break communication between these people in a large organization, also some of the work that we've been doing, you will get evilish corporations, right? So it's an emergent phenomena that you have to be very careful about, and especially in healthcare. When you design systems, you're talking about agenting systems with tens, hundreds, thousands of different agents. In healthcare, we got to be careful of how these interacting systems work, right? And let's see how we could build a framework around actually doing this. So before we get into a specific use case, which I will take you through, I want you to be aware of a few key systems thinking principles, and we will build on that as we go forward. So first topic is when you build a system, you start whiteboarding, and then you put these nodes on, which technically we would call stocks or batteries, or variables in this context, and you draw arrows from, let's say, A to B. And you can think of this as a causality. A causes B to happen. Okay, then I draw an arrow from A to B, and then I add little polarities. Does A increase B or A decrease B? All right? And the other few concepts are delays. When A does something to B and B has to do something to C, it may not happen instantaneously. There is a delay. And delay is a weird thing, especially in healthcare. It's very important to keep delays in mind, because when you give a medicine or a therapy or something, you don't expect instantaneous change. And you cannot sit around for change to happen, okay? And and the other concept is, when we looked at this, what we saw was a simple diagram. This is a real use case. where you built an entire, what we call causal loop diagram for the COVID pandemic. As you can see, the healthcare system in gray is right in the middle, but you have then very heterogeneous systems. You have the social system, you have the health, you have the environment, you have the economy. When you whiteboard what is causing what, you don't have to worry about making these nodes homogeneous, right? You have different sectors, and they all play a role, and this entire thing acts as a system, right? And this gives you a sort of a clear overview of what's happening to your whole system. Now, of course, as you can imagine, this needs a lot of expert knowledge, domain knowledge to build it. And in healthcare, when you're, creating funny cat pictures, that's okay. You can go back and correct it. Or you want to do some creative things, or even build code. You can test it out, go back. But when you build applications, especially for healthcare, this is mission critical, right? So involve the stakeholders from the very beginning. The stakeholders with patient in the center. Please don't forget it. So as soon as you start building a system, you try, as in discovery phase, get the patients involved, physicians, policymakers, and if you're in a hospital, all the C-suite of the hospital need to involve in building that application. So wanting and designing explicitly with expert knowledge baked in is not a bad idea. And for those of you old enough to remember, there was a whole field of expert systems, and I am sort of calling that back in the age of agentic AI. So the other concept, key concept, is boundaries. So boundaries is to know when you don't know. And that is extremely key. So LLMs, machine learning algorithms, you ask it something, it will give you an answer. It is very difficult for it to say that I don't know. You need to build that into the system as well. And boundaries help you do that. So for example, I give you an example. So I want to build a system to help employees work better in your company, right? To be motivated and so on. You have control on the feedback you give, the workload you give it to them, the holidays, the employee benefit package and so on. But you don't have control over what happens out in the world, the wars that take place, the macroeconomics, even the family life. So when you build a system, make sure that you know what you're dealing with, right? And this is very important. And then there's this concept of leverage points, okay? This is, again, policymakers, public health. You start thinking about these things because leverage points can be classified in sort of the level of difficulty from 1 to 5, 5 being more difficult, is that if you want to change a system, leverage points are the ones that if you tweak a little bit, you see a big change in the output, all right? And of course, it depends. If you want to do simple things, relatively simple things that, build better efficiency in the system, you can change reporting lines, for example, in your organization. But if you really want to bring about a new culture, you have to change the mindset of the entire organization. And that's, as many of you might know, is not trivial, right? And so the harder, the lower you go, the harder it gets. But keeping these points in mind, and when you design a system, if you know to identify this is the first key point, right? You can build sort of strategies to tackle this. So now, what I wanted to do is, now that you are experts in agentic AI and systems thinking, we will go into a very, very specific use case. And this use case is sort of tangential to some of the things that we're working in. But more importantly, I want this use case to serve as a template on how you think about designing such robust and sort of verifiable systems, if you wish, right? So what we're going to build for this use case is actually a high risk. So if you go out as a startup and want to build something like this, you have to follow some of these principles, right? So getting something like this approved is not going to be easy. So this is what we would consider sort of a high-risk application. So what is the application? Heart failure home care app, all right? So let's go about building. So imagine that you're pitching to somebody. What is this, right? So meet Anna. She is 68 years old and just been discharged after being treated for heart failure, decompensation. Basically, the heart is not able to pump enough blood in the body, right? And but now she's okay. She's been discharged. She's back home, and she needs to be cared for. And our job is to build an agent, and its job is to keep Anna euvolemic, in the sense that she is enough blood in the body and there's enough fluids in the body to keep her healthy and out of the hospital. So there is a key interesting fact that I want to highlight here. That is, the goal is not very quantifiable. Keep her out of the hospital is the goal. And that is quite human-like, all right? I'm not saying make sure that the probability of her coming back to the hospital in 30 days is 0.97, because that's not the way you interact with humans. If you have a human caregiver at home, you would say, take care of her because she has this problem, so keep her fluids and body in check and make sure that she is able to stay at home without needing care in the hospital, okay? Because it's a big, and make sure that you do this in a safe manner, not by holding her and keeping her in the bed, right? So how do we do this? Now what we will do is go through some of the design principles that we briefly touched upon, but then we will go through for this specific app, okay? We start with now, how do you say what is the environment and boundary in this case? So the environment is very simple. It's Anna's house, and all the sensors that she's wearing. Can be wearables, blood pressure cuffs, electronic health records, and also, importantly, the caregiver or the care team that is in the hospital, right? And the boundaries should be correctly measured. What it cannot do is important, right? You don't want it to prescribe or change medication, because that's why we still have physicians and doctors in the hospitals being trained to do this. But what it can is give nudges, give message to Anna, schedule telehealth, propose different things that she can do so that her her state is kind of stable, right? Now, what are the sensors in this case? Same thing. What's the daily weight that you can measure? Heart rate, blood pressure, all of these things that the agent has clear access to, right? And a state, for those of you in signal processing, it is similar to something like a Kalman filter, right? The idea that you have noisy inputs and you have to predict that state, 1 hour from now, 1 day from now, pretty robustly with uncertainty bands around it, right? This is what the agent needs to do. What are the sort of actuators? What are the tools that it can use, right? What can it do to enforce something in this world? Coaching, tell Anna to, walk for 10 minutes after the meals, or do some very light exercises. Again, it has to be carefully administered, right? The ability to reach out to a human when necessary, ask for lab reports, or actually conduct, tell your care agent you should be checking into this, which is not there at home, and so on and so forth. It should have some know-how of the way the processes work, right? This is where the causal loop diagrams actually come into play. Clear goals. Here is very an interesting concept as well. Clear goals is to make sure, of course, that because she has undergone this operation, to make the fluid status in the safe range by having some additional constraints to make sure that your kidney is functioning well, your blood pressure is good, and so on and so forth. And also make sure that you don't keep nudging, you don't keep notifications on all the time. It should be sort of more human-like, right? But at the same time, you have to preserve privacy and consent. And what are the signals that we're looking for? All right? We don't want Anna to go back to the hospital. That's the key thing, right? Number one. The rest is the symptoms have to be managed. The lab reports have to be stable, right? And avoid any kind of false alarm. You don't want to call in the ambulance for no reason, or conduct excessive studies, because it's a burden not only the healthcare but also on Anna. And this is what I call the world model. So it has to have some understanding of the medical sort of field for that, at least for that particular problem, okay? Which, to know when does the fluid volume go up, what happens if I have diuretic pills, and so on, and how does it dynamically affect the patient, right? And also to understand the other thing that I told you about, delays. So I've given this medicine to Anna. How long does it take for that to act, okay? So that building in that kind of time delay component into the system. So again, there are many more design principles that you will follow. Eventually, you will reach, so budget is important. Budgeting not only in terms of money, but in terms of attention budget of the patient, nurse time, compute, cellular data, so on and so forth. Every single aspect has to be built in. So you don't have to look at the whole slide. The idea is that you can build an agent for all of these different design principles that we went through, right? And I just want to highlight two. For example, you have an agent which is an engagement coach. Now that has to be done very, very specifically for that purpose alone. And it has to be given all these constraints and guardrails and what are the actions it can perform. So remember that how breaking up the whole problem, instead of one LLM trying to do all of these together, you have each one of them which we have good control over, doing each of these different tasks. And making sure there is an orchestrator agent that is able to sort of decide which of the agents gets which kind of task and how to interpret that task, right? And this orchestrator often can be a bit more sophisticated agent, which could also actually live on the cloud instead of on the device. So eventually, at the end, it should look simple. When it comes to the user, when it comes to the care team, you should have an app which has basically all the parameters you want to see, a quick dashboard to see, how stable is the patient, and so on and so forth. When is the next visit? It should be a clean design. But what is powering this underneath is this entire design structure we talked about, okay? With exact knowledge of the causal loops, what happens when something shuts down, what happens when there is imperfect information, what happens when some of the sensors don't work. It often happens. Not always she's going to have the wearables in her hand. So having an explicit diagram that sort of encapsulates all of the things that we talked about gives us a good idea of where are the leverage points, where are the break points, and how to design this entire system. So what happens when we don't get it right? So this is a simple example, not simple, but So for example, if you build a naive agent versus a budgeted agent, what could go wrong, right? I'd like to highlight on this aspect that I brought up earlier on delay modeling. So on the top right, you see what happens when the agent is not able to wait to act, to know that there is a delay. What it does is, the weight is decreasing, let's give her more fluids. The weight is increasing now too much, let's give her diuretic pills to get the weight down. And you get these oscillations. And these oscillations are not just in this app. The oscillations happen in the real world in complex systems, right? A great example of this is in politics. Often you have these 5-10-year cycles when everybody goes to the left. Left goes crazy, everybody goes to the right, right goes crazy. And this is a well-known phenomenon in complex systems, these oscillations, right? And it's not well defined, but there is a oscillation budget. You have to be careful. The more oscillations it has, at some point the system breaks. So the whole idea is to reduce the oscillations, at least mitigate the amplitude of the oscillations, right? This is exactly what happens with, you want to maintain a weight, you have to have a band between which the weight has to go. And this can be done only if you have that concept of delay set in, right? So don't overdo things, wait and see. This is exactly what your physicians do as well, right? So there are many other examples of what could go wrong if you don't use systems design principles, right? So there are a few advantages that I wanted to highlight. So one is, like you saw in the example with the COVID response or the effects on different components in the society. We had it all in one whiteboard. You can do the same. One of the biggest issues, honestly, there is enough technology today to make great inroads into innovation in healthcare. We have the technology. We don't need to invent a lot of things, but we need to innovate. All right? We do need to innovate because what we don't know essentially today is not about how to build a good system, but how to embed that system into the workflow of the hospitals in a way that is seamless, right? And when you have these whiteboarding sessions where you build the agentic architecture, you can use the same whiteboard, the same concepts, the same causal loop diagrams to see how does a clinician fit into the whole picture? How does the patient fit into the whole picture? So you can have, just like in the center, you have the patient, you have the clinician, you have the AI agent, you have all the other things in the environment that could go wrong and that could go right. And think about all the reinforcing loops, all the virtuous cycles, all the vicious cycles that might happen in this kind of a large causal loop diagram, right? So it really helps in implementation science. So as when we talk to hospitals, we have these things where it works great, but it'll be great to know exactly how to bring them into the picture. Domain knowledge is baked in. So some of them are like, oh, LLMs can do everything, it'll figure out new things. No, before we figure out new things, let's get the things that a lot of humans spend their sweat and blood, and then sort of transport them into the world of AI agents, keeping most of the workflows the same, right? That itself will add billions and billions of dollars of value in the current state. So before we go all crazy on LLMs, discovering new things, let's get some of these workflows baked in, right? So domain knowledge, please work with experts. Experts are not necessarily AI experts or developers or coders. Work with the real people that you're trying to help, right? A clinician or a patient at the center. Grounding is a big problem. There are a lot of explicit ways to. When people talk about grounding, is essentially mapping some of the responses of your AI system to something that you know is true in some ways. So you use image to ground your LLM and so on and so forth. And this kind of dynamic graphs helps ground your agentic systems, right? Interpretability is big, especially in the healthcare system. You want to know if I don't do A, B, C, what's going to happen. So when you have this entire system built in, you can switch off each of these components and see what the system does, and you have direct control. You do have ablation studies when you talk about pure deep learning, but that gives you a vague understanding of what the representations might be. But here, if I don't have a particular measurement, is that crucial, or is it okay for a time being? Because you'll have to deal with real-world data here, right? And finally, I can tell you that if you are a startup, if you're a builder, and if you want to build a system, this would be considered high risk, this app that we just went through. And this follows very closely some of the principles of SAMD, which stands for software as a medical device. So if you want to build this out and sort of scale it, you will be required to follow some of those, and this would make life for FDA and so on easier to accept your app, and you will be more compliant to many of these FDA rules and GDPR and HIPAA compliances and so on and so forth. So before I end, I just want to, so those of you who are more deep into the tech, this is closely related to the idea of knowledge graphs. So knowledge graphs are becoming very ubiquitous these days. The idea that all of your knowledge can be stored not just as vector databases, but vector databases with connections that make sense, which often are built by your human expertise. And you can think of this as basically the knowledge graph is like a map, and what you're doing with systems thinking is bringing in some kind of temporal aspect, some kind of dynamism, some kind of life into that graph, so that it is grounded not only in a particular snapshot, but it's also grounded in how to think temporally. And all decision-making tools, inevitably, has to have a temporal component in its background. Otherwise, you're not going to build anything that works reliably over time, right? And future directions is my last slide. So agent-based modeling is very different from agentic AI, but these principles can be used to build better agent-based modeling, especially if you have at the scale of the whole population, trying to build sort of a digital twin of the entire population in a city and so on. These principles really help in exactly grounding the kind of inferences that come out of the LLM. All right? And there are other ways of smoothing out these kind of interfaces that I talked about, many agents talking to each other. The problem, again, mathematically, is if you build one neural network, right? If you have an error signal, you can propagate that all the way through the neural network. When you have multiple agents, it's not clear how the errors will propagate, right? Because it's not differentiable in some sense. And again, using this can help you build better products for the real world, all right? And that's it from me. Any questions? Thank you.
Thank you, Dr. Thomas. We have time for 2 questions. Please keep your questions brief.
Hello, everyone, and good morning. This is Dr. Mohammed Baraka, Associate Professor of Clinical Pharmacy and the former Dean of Pharmacy at Fatima College of Health Sciences. Today, when we want to take a decision regarding certain disease state, in the hospital, for example, we have a round of 6 healthcare providers discussing together, having guidelines to guide their decision-making, and having a reasoning process and a discussion. In the future, I will not be surprised within 2-3 years to have multi-agent platform attending the round with us. And here, the decision, in my opinion, will be totally different. Because in the current state, we have the guidelines that we go back to, and we have our reasoning process. While having the agent on the table, we will have different type of information, a massive amount of information coming from the wearables and sensors, and 360-degree sources of data of the patient. And now we are thinking about the personalized health, even not personalized medicine. And I believe in the future, the agents, or this multi-agent, when we saw the interaction between these agents, I believe they will generate a totally new type of knowledge here that is beyond our capacity to say whether this is right or wrong. How do you see the future of evidence-based medicine in this case? And how do you think the future of education should be in order to cope with such changes? Thank you.
Yeah, thank you for that nice question. And taking your question last, we at Cornell, of course, we are primarily an education institute. We think a lot about actually redefining a medical curriculum, which is not easy because it's like a dinosaur. Very difficult to be agile there. But times are changing. I can tell you how. When I joined a year and a half ago, and we have this kind of a special program called Area of Concentration, I had 1 or 2 students approaching me. This year, I have 40 students saying, I want to do a project in AI. Okay, so these are young students who in 5-6 years' time will be your physicians, right? And they are getting really interested in this topic, which is a great topic because this is going to stay. The way I think about it in sort of evidence-based, like you nicely articulated, is a doctor now not needing to have sort of those kind of meetings with other experts all the time. Whereas you as a specialist in endocrinology, for example, have agents which are pretty good at many other disciplines. And if you want to ask a particular question, you can't afford to have all the experts all the time just next to you, right? So the idea of you getting a preliminary diagnosis, at least, from these agents, and you're saying, okay, then you make your expert opinion, okay, this seems real. Let me then go talk to the expert if it's necessary. But if it is in line with what you're thinking, you go ahead. So you'll have to make a lot of sort of human discretion comes into the picture for a doctor. But then the doctor has to learn to interpret when to believe and when not to believe. And I think that is the most important thing that we need to teach our future physicians on how to use the system as a co-pilot in healthcare.
Thank you, Dr. Thomas, for your talk. I'm sorry, but in the interest of time, we'll have to cut to the lunch break. Unfortunately, we have a shorter lunch break today, but I'm sure Dr. Thomas and Dr. Kabot will be around to answer any more questions. Before we head out, just a note that if you would like to learn more about ADIA Lab's work in health sciences, please feel free to connect with me today or tomorrow. Now, lunch is served outside, and we'll be reconvening here for the afternoon sessions at 1:30 p.m. Thank you.